Besides the thermal heat transfer side of mechanical engineering and the study of fluid mechanics and thermodynamics, we also have the machine design side of mechanical engineering. And so in Chapter 11, we studied material behavior. That's an important component to choosing what material you're going to use depending on the purpose. For our focus, we're going to be looking at gears, although there are a variety of machine elements: gears, shafts, bearings, fasteners, springs. You can see the list there. And so in gears, what we're looking at is things that are rotating. And so we need to be able to measure the speed of that rotation. And there's a couple ways that we can do that. One is in the number of revolutions per minute. We'll use the capital N variable. And then there's the angular speed. And so that's the Greek letter omega, not a W. And so that's measured in radians per second. And so we need to be able to convert back and forth between those two. So if we start with omega being radians per second, and we want to start on the other side with N, which is in revolutions per minute, putting it in a fraction form so it's more units based. We want to convert those revolutions per minute into radians per second to see what the relationship between these two are. So to start off with, we can convert the minutes into seconds easily enough. And then one revolution is just one circle, so we can say that one revolution is the equivalent of 2 pi radians. And so then we can kind of clean this up a little bit into an equation where we've got omega equals 2 times pi times n in revolutions per minute all over 60. So this is an equation that we can use to jump back and forth. If we know what the angular speed is, we can find what the revolutions per minute are. If we know what the revolutions per minute are, we can figure out what our angular speed is. So we often want to take the rotational speed that's happening inside of a motor or an engine and translate that into linear speed. So for linear speed, our target is to end up with units of meters per second. So if we start off with the circumference of whatever rotating object we have, we're going to have 2 times pi times r, and so we can express that in meters per revolution. So every revolution, a point on that rotating object is going to travel 2 pi r meters. And so then if we take that and multiply it by n, which is in revolutions per minute, we're getting close. So our revolutions cancel each other out. Now we have a length, meters, except it's over minutes instead of seconds. So we can make that conversion with 1 minute over 60 seconds. And so now we've got meters per second. And if we rearrange this slightly, we've got r times 2 pi n over 60. Now hopefully this part here is familiar to us from our previous work, and so that means that we can either express velocity in terms of the revolutions per minute using the equation that we have up above right now, or we can substitute the angular speed for what's in the red bubble there. So we can say that the linear speed is equal to whatever the radius of this particular rotating object is times its angular speed in radians per second. So a car engine typically has its rotational speed anywhere between 0 and 7,000 RPMs. Of course, the wheels aren't going to be moving that fast. So in fifth gear, while we're cruising along the highway, when the engine's rotating at 3,000 RPMs, we've got a car traveling 100 kilometers per hour. We've got the tire diameter of 0.8 meters. So we want to find what is the angular speed. Remember, that's in radians per second. And then we want to find the rotational speed of the tires in RPMs. So we'll start with the equation that we just defined for ourselves. So we've got V equals R times omega. So we've got our velocity is 100 kilometers per hour. And then that's equal to, remember, it's the radius that we need, so 0.400 meters times omega. So if we multiply both sides by the reciprocal of this guy right here, we're going to end up with omega. And so we've got 100 kilometers per hour times 1 over 0.400 meters. Now, for our units, what we want is this radians per second. So radians are essentially a dimensionless quantity. So we just need to get these lengths to disappear, and then we've got to convert these hours into seconds, and then we're going to be in business. So we can use the conversion of 1,000 meters over 1 kilometer. So that will get these kilometers and meters to all disappear. And then I just need to convert those hours into seconds. So I've got 1 hour is 3,600 seconds. And so if we multiply this out, we ultimately end up with a result of 69.4 radians per second. So that's our angular speed. And then we want to convert that into rotational speed. And so if you recall, we have our equation omega equals 2 pi n over 60. So we can rearrange this by taking our 69.4 radians per second. I can multiply both sides by 60 and then divide both sides by 1 over 2 pi. And so then we end up with an RPM measure of 663. So we've got 663 revolutions per minute for the tires of that diameter to get us moving at 100 kilometers per hour.